one of the questions, and we certainly could not do that question. That was from, I think, yeah, here it should be the question. This was the last question, right? At a certain depth d, no, not this one. Yeah, this was the question. If the gravitational field in the space is given by minus of k over r cube, taking the reference point to be at r equals to 2, with the gravitational potential V equals to 10 joule per kilogram, find the gravitational potential at R equals to 3 centimeter in SI unit. So for this, we will take the help of the electric field that you have studied. In the similar way, we will try to do it for the gravitational field. Okay. What quantity we are given here? The gravitational field in space. So we have been given the gravitational field. Let us represent here gravitational field also with the symbol E. So in electric field, you have studied at one point that electric potential or dV is given as E dot dr. Right? So this is what we call as the electric potential is given at E dot dr, or we have done another concept, dV by dr is equal to electric field. Do you remember this concept? That the potential gradient is equal to the electric field. Okay. In the similar way, if we apply the same definition over here with respect to the gravitational field, if the field is your gravitational field, so then we can say that the rate of change of gravitational potential with respect to the distance should be equal to the gravitational field. So we can make this as dV, which we consider here the gravitational field, with respect to dr should be equal to the gravitational field, and the gravitational field at any point in space is given by minus of k over r cube. So from this we can get our dv to be equal to minus of k by r cube. So k by r squared, it's not r cube. Every time I'm writing cube, it's k by r squared. So minus of k over r squared, and here we have dr. Now, to find out the value of potential, we know the potential at R equals to 2 is 10. Okay. So, we will use this definition to integrate and find out the potential difference between the 2 points. So, if we integrate both the sides, dV and this minus k by R squared, so R varies from 2 to 3. R varies from 2 to 3. And at 2, when R is 2, we know the potential is given as 10. And we want to find out the potential at R equals to 3. Let that potential be V. So we will use this, and now we can integrate. So the integration of dV would be given as V, and its limit of integration is from 10 to V. Then we obtain here minus K is the constant, and we have to integrate this. If we have to integrate 1 by r squared dr, the limit of integration is r equals to 2 to 3. So any doubts here? I hope you are able to get this concept. We are using the concept of the similar to the electric field. In the same way, we can also use it for the gravitational. Okay. So here we have used this concept, and we try to find out this. So if I integrate on this side, I will get minus k as it is. And integration of r squared would be r cube. This would be r to the power minus 3. Sorry, not minus 3. It will be minus 2 plus 1. So you will get here minus 2 plus 1 as the integration. Minus 2 plus 1 and divided by minus 2 plus 1, that is minus 1. The limit to be reached from 2 to 3. So you have, if you take this minus over here, you can get plus. You will get plus k. So here we will have, on the left hand side, we will get v minus 10 by applying the limits. And on the right side, we will have k over r, k multiply 1 over r, limit from 2 to 3. So again, we write upper limit minus lower limit and then try to solve the values. The value of K is given to us. K is given as 6 joule centimeter per kilogram. So we'll convert this and then we will utilize these values. Okay. It's 6 joule centimeter per kilogram. And to utilize this, we will be using everything in the SI system of units. Since we want our voltage in the SI system of units, so we will be using our R also in meter. We will use the value of K also in meter. Okay. And then finally get the values here. So let's take it. We have V minus 10 equal K times of 1 over R and from 2 to 3. Okay. Now, if even if you convert the value of K, see K is in centimeter. So if you put, you can write here K. Let's put up the value only. So if you put K is 6 joule centimeters, you to convert it to meter, you can multiply it by 10 to the power minus 2. But similarly, if you apply the definition here, you will have 1 by R, and R is 10 to the power, R is in centimeters, so it will be 3 multiplied 10 to the power minus 2 minus 1 by 2 multiplied 10 to the power minus 2. I hope you are getting, since these 2 and 3, they were in centimeters, so we have put them in meter. And now you can take out 10 to the power minus 2 common, cancel it from the numerator. So ultimately you will get this one only, 6 multiply 1 by 3 minus 1 by 2. Now taking the LCM, you will get here 6 multiplied with 2 minus 3 over 6. So again 6 and 6 cancel. So you get V minus 10. V minus 10 equals to minus 1. And hence we have uh, sorry, 2 minus 3. So okay. So V minus 10 equals to minus 1. And hence we can get here, if we transpose this minus 10 to the other side, we get V equals to 9. So that's the answer. You can see here we have one of the options as 9. So that's the answer. Answer 1 is the answer. Okay. Any doubts here?
No, sir.
No. So you can try this question. Now there are a few questions in which we are asked, find the gravitational potential energy of the system of masses. If you are asked the gravitational potential energy of the system of masses, like we have one question from NCERT, gravitational potential energy of the system of masses. We have a question regarding, so we also have a question here which is regarding the orbital velocities. So orbital velocity or the escape velocity. If you find any question, I hope we will be able to do that. Let's see these questions. Okay, so we had done this question number 12 we had done. This is 11, 12 we have done. Let's see question 13. Spherical insulating ball and spherical metallic ball of same size and mass are dropped from the same height. Choose the correct statement out of the following. Assume negligible air friction. The time taken by them to reach the Earth's surface will be independent of the properties of their materials. So is this true or false?
False.
Why? What difference will be there? See, they have given that there is no air friction. If there is no air friction, so we will get the acceleration due to gravity will be same for both the balls. And if acceleration due to gravity is same for both the balls, so they will take the same time. And hence, if you
Yes,
observe
sir.
the first statement, the time taken by them to reach the Earth's surface will be independent of the properties of their materials. Okay, so statement 1 is correct. Insulating ball will reach the Earth's surface earlier than the metal. This is false. Both will reach the Earth's surface simultaneously. So is this true or false? This is true. Both will reach the Earth's surface same time. So this is also true. And metal ball will reach the Earth's surface earlier than the insulating ball. This is false. So you have correct options are option 1 and 3.
Okay, sir.
A body weight W is projected vertically upward from Earth's surface to reach a height above the Earth, which is equal to 9 times the radius of Earth. The weight of the body at that height will be. So I think now this question does not need any explanation. You can solve this out. Can you solve this out? A body weight W is projected vertically upward from Earth's surface to reach a height above the Earth's surface, which is equal to 9 times the radius. Please, okay. So can you do this question? Can I get your answers?
Yes, sir. One moment.
Okay.
Sir, is the answer option 2?
Uh, Answer is say option 2. Okay. Yes, let's check out. I think it should be correct. So the formula is correct here. G dash equals to G minus G multiply 1 minus H by R or minus 2.
Sir,
G plus. Okay, it's 1 plus, right? So you have 1 plus H is 9 times of R. So you have 1 plus 9 whole squared. Yeah, so you are correct. Your answer is this W by 100. Okay. So now I think you have understood this gravitation. We can start with the next topic in the next class. We can start with SHM in the next class. Acceleration due to gravity is different at different places on the surface of Earth. So is this statement true?
yes, sir.
X. Yeah, it is true. Why that acceleration due to gravity is different at different places on the surface of Earth?
The acceleration depends on the latitude.
The acceleration depends on latitude. Yes. And about the second point, acceleration due to gravity increases as we go down below the Earth's surface.
Sir,
In
this
the
is
light of,
false.
okay, this is false. It increases. So you have statement one is true, but statement two is false. So that is option 3. If Earth has a mass 9 times and radius twice to the twice to that of a planet P, then VE by 3 under root x meter per second will be the minimum velocity required by a rocket to pull out the gravitational force of P, where VE is the escape velocity of Earth. the value of x is. So what should be the value of x? So this question, as we discussed, that it is related to the escape velocity of a planet. So what is the formula for the escape velocity? How can we find out the escape velocity? Okay. See, the concept of finding out the escape velocity is that whatever is the binding potential energy, whatever is the binding potential energy of the planet or of the Earth, so that should be equal to the kinetic energy possessed by the satellite. So then only the satellite will be free from the gravitational pull. I get it. So the binding potential energy of, as we know that the potential is given by the formula minus of Gm over, yes, the potential is given as minus of Gm over R. This is how the gravitational potential is given, and the gravitational potential energy U at any point is given as, if you multiply this V by mass, so you'll get the gravitational potential energy, which is minus of Gmm over R. Okay, but since we are talking for the, so for the surface, so this R should be equal to the radius of the Earth. This is what is the gravitational potential energy. Now, for the escape velocity, this gravitational potential energy should be equal to the kinetic energy. So this Gmm over R should be equal to the kinetic energy. So you should have 1 by 2 mv square should be equal to this. And now from this expression, we found out the value of escape velocity. So here we get the value of escape velocity as 2 gm over r and whole squared square root as the escape velocity on the surface of. So you can see you have an expression for mass also, you have an expression for r also. Okay. Now how we will relate it with the new planets? So you can, if you multiply it by r and divide by r, there are different things that we can do here. But this is the expression for the gravitational potential for the escape velocity. So on the Earth surface, this is the value of escape velocity. Let us see the escape velocity on the planet. So escape velocity on the planet would be given by under root of 2g multiply mass of that planet. So what is the mass of the planet? If Earth has a mass 9 times and radius twice that of a planet P, okay. So Earth has a mass 9 times of that, or 9 times of that planet. So that planet will have a mass of m by 9. M by 9 would be the mass of that planet. Okay. Earth has 9 times of that mass. So the mass of that planet would be m by 9, and hence here radius is also given. So radius twice to the that of planet. So radius of the planet would be r by 2. If Earth has the radius r, so the planet would have a radius r by 2. So you can write here r by 2. So 2 will be here in the numerator. Now you get here 4gm over 9r as the escape velocity on the planet. Now, if I relate this whole thing with this one, if I relate this whole thing with this escape velocity, so I can write this as under root of 2gm by r and multiply by 2 by 3, multiply by 2 by 9, under root of 2 by 9. Okay. So, if you take this under root of 2 by 9, the square root of 9 is 3. So you can take this actually out, and from the expression we can write under root 2 gm by r as the escape velocity on Earth VE, under root 9 as 3, and we can write here under root 2. Okay. So if you compare these two expressions, what should be the value of x?
It should be 2.
It should be 2. Okay. So just a clear understanding of the concepts. We have calculated the escape velocity. We know the escape velocity. Okay. But we do not know how to find out. So here, okay, so we can find out this escape velocity in this way, just utilizing the concepts. Even if I did not remember, I do not know the formula of the escape velocity. So I know that to escape, we need to provide the kinetic energy, and the kinetic energy should be equal to the gravitational potential energy. Since it is a gravitational potential energy which is binding the substance, which is binding the satellite. Okay. So if you have that sufficient amount of kinetic energy, you will escape out from this. So this is your escape velocity. Let's see some other questions, or I want to see one question from NCERT, and then we can move on. Just let's see. Just 1 minute. Let me check out if I can get one question, and then we can move out of this chapter. So from this chapter, you should be knowing about the law of periods, that is Kepler's laws. You should be aware of variation of G with height and depth. You should be aware of gravitational potential, gravitational field, and gravitational potential energy. If you are clear with these concepts, you can move on further. Okay, let's say this is one of the questions I would like to have a look. Three equal masses of m kilogram each are fixed at the vertices of an equilateral triangle ABC. What is the force acting on a mass 2m plus the force? Okay, so this we can find out. There is no problem here. This you can do. Can you do this question? I don't think that there is some problem in this question. Okay. So all this we have done. Variation of acceleration due to gravity we have done. Gravitational potential energy also has been done. Okay, let's see. This one I want to discuss with you. Example 8.3. This is a pretty good example clearing all your concepts. So you have to find the potential energy of a system of four particles. Find the potential energy of a system of four particles placed at the vertices of a square of side L. Also obtain the potential at the center of the square. So you have to find out the potential energy of the system of four particles placed at the vertices of a square. You take a square here and there are four masses which are situated at the four corners of the square. These are the four particles, and the square has the side L. This is the side L of the square. और डायग्राम कहाँ से देखो? पैर एक बार देख के ट्राई करना. This is your mass M. This is also mass M. Okay. So any idea how we can find out the potential energy of this system? Yes?
I'm not sure, sir.
Not sure. Okay, so let us try to make this system. Consider that these masses are located at infinite distance from each other. So initially we have just a mass m. So we have a mass m over here. And now we are bringing the second mass m. We are bringing here the second mass, which is located at a distance l. So I want to bring it. This one I am bringing from infinity to this point. Okay. So the amount of work done or the gravitational potential energy of this system would be given by potential at this point. Let's say this is your point A, this is your point B. So it should be equal to the potential at this point due to this mass at A multiply by the mass. Okay. So I can find out potential by the expression of potential as minus of Gm over R. So this represents the gravitational potential at this point. The distance R is actually equal to L. So I put here L. Now the potential energy at this point, the gravitational potential energy at this point would be equal to minus of Gmm over L. So it is minus of Gm squared by L, right? So at this point, this system has the gravitational potential energy given by minus Gm squared by L. Here I have assumed that all the particles are similar. Even if I take the all particles to be different, so it will be just M1, M2, M3, M4. In that way, it will come. So here I have taken all of them to be identical. This is the potential energy of this system. Now I bring another mass. So here I bring another mass at C, and this mass I am bringing again from infinity. So the amount of potential energy now the system will hold. So it will be this potential energy which it is already holding, plus it will have some work done by this charge A, by the mass A, and some by this mass B. So the gravitational potential at this point C can be defined. If I want to find out the potential at C, it will be due to the two masses, due to the mass A and due to the mass B. And as we know that potential is a scalar quantity, so we can add them. We do not need the vectors. We can find them out with their positive, whether they are positive or negative. Since the gravitational forces are always attractive in nature, so the gravitational potential will always be negative. So gravitational potential will always be negative. So I can find out the gravitational potential at this point C. The gravitational potential at the point C would be equal to the sum of the two potentials, one due to the potential of A, one due to the potential of B. So potential at C due to A would be equal to minus of Gm over, and this distance would be equal to under root 2L. So this is under root 2L, plus you will get the potential due to B, which is again minus of Gm over L. So this should be the total potential, and the total potential energy of this system would be equal to multiply this whole thing with the mass m. So you will get here minus of Gm squared over L, and inside the bracket you will get here 1 by root 2 plus 1. This is the gravitational potential energy now. Okay. Then now I bring another mass. So can you find out now? So if I bring another mass here, let's say I bring another mass D over here. So now the potential energy at this point would be the sum of all the potential energies. So again, in the similar way, I will find the potential at D. Potential at D due to the individual masses. Potential due to A, potential due to B, potential due to A, potential due to B, and potential due to C and D. This I need to find out. Okay. And then in the similar way, I add them. So I will get the potential energy. And if I add up all the potential energies, I will get the total potential energy of the system. So have you understood?
Yes, sir.
Yeah. So in this way, I can get the potential energy of this due to A, due to B, and due to C. Potential at D would be given by first potential due to A, V due to A, V due to B, and V due to C. So V due to A is will be equal to minus of Gm over L. Potential due to B will be equal to minus of Gm over root 2L, plus potential due to C will be minus of Gm over L. So again, you can get here minus of Gm by L common, and inside the bracket you will get here 1 plus 1 plus 1 over root 2. And hence, if you get the potential energy at D, so you can multiply by M, so you'll get minus of Gm squared over L. And here we get 2 plus 1. So it's 2 root 2 plus 1 by root 2. Now, the total potential energy. I want all the potential energy. So that will be the sum of all the potential energy. That means the potential energy of B, the potential energy of C, potential energy of D. So if all of them added together will give me the total potential energy. Okay. So let's find out the total potential energy. So what concepts are to be utilized? That first thing, you have to see that the gravitational force is always attractive in nature, and hence the gravitational potential, it will always be negative. Okay. But the change of potential or change of potential energy can be positive. If you take a mass from one point within the gravitational field to a point away from the gravitational field. Okay. So if you take it away from the gravitational field, then you will be getting a positive change of potential energy. You will be getting a positive potential energy. Okay. So now this is for D. In this, I'm adding for the previous one which I obtained for C. So this is minus of Gm squared. This is minus Gm squared by L. And here you have 1 by root 2 plus 1. So you have 1 plus root 2 by root 2. Here we have 1 plus root 2 by root 2. And then the next one, that we have minus of Gm squared by L. So this is minus of Gm squared by L. So I hope you have understood this question. In the similar way, you can find out the potential energy of any system of masses.
Yes, sir.
So in the similar way, you can try out to find out the system potential energy of a system of masses, which is found by in the form of an isosceles or equilateral triangle. The masses which are located as in the isosceles or equilateral triangle. So see, this is what we have got here in the answers. Okay, you add up all of them, and finally you will be getting this is what is the answer. So you can check it out by obtaining the final answer, and you can get the total potential energy of the system. Escape speed or escape velocity we have already done, that whatever is the binding velocity, whatever is the binding potential energy, we must provide at least that much of the kinetic energy so that it can escape. Then if we find out the orbital velocity, yes, yeah, this question is also very important. I want you all to do this question as the homework. See this question. So two uniform solid spheres of equal radii r, but mass m and 4m have a center to center separation of 6r as shown in figure 8.10. The two spheres are held fixed A projectile of mass m is projected from the surface of the sphere of mass m directly towards the center of the second sphere. Obtain an expression for the minimum speed v of the projectile so that it reaches the surface of the second sphere. Okay, so this question utilizes very good concepts of your gravitational potential energy and the null point. Okay. Do you remember the null point we discussed? The null point was the okay. So bye everyone. I'm sending this out. You can do this as part of your homework. Okay.
Okay,
I
sir.
hope you will try this out. And in the next class, we will be starting with SHM, simple
Okay, sir.
harmonic motion. Okay. Bye.
Thank you, sir.